Hello, Pradeep, I am audible.
Yes, sir, you are audible.
Okay. We'll wait for 5 minutes, then we'll start.
Right, sir.
From the previous doubt was the buoyancy force and all. We'll
That's
discuss
good.
first, then we'll go for the boundary layer approximation.
Okay, sure. Sure.
Okay, Pradeep, we'll start. If someone join, then okay. Hello, Pradeep, I'm audible.
Yes, sir. Yes, you're audible, sir.
Okay, we will start from the basics of the previous whatever was doubt. Let me take the okay. Well, welcome in the week 11 fluid mechanics live TA session. The week 11 was about the approximate solution of Navier-Stokes equation, and in this lecture 1 was about the boundary layer approximation first and boundary layer approximation second and boundary layer approximation 3. Basically all this 11 week was dedicated for the boundary layer approximation. Why boundary layer approximation is important and how it come in the picture and when it come in the picture. Before the boundary layer approximation, what was the approach for solving the fluid mechanics problem, and after developing the boundary layer approximation, what are the approach. So we'll see all these things in this in this lecture. Before going on this boundary layer approximation, one student uh, one student was having the doubt about the buoyancy force, and basically the question related was the buoyancy, stability, and the rotationality and pitching kind of thing. We have discussed first on the buoyancy and stability, then we'll go for the boundary layer approximation. And I have some question like related to the boundary layer. So we'll solve the question also. So buoyancy and stability. Basically, Pradeep, my voice is clear.
Yeah, yes, sir. It is very clear.
Okay. Now it is visible. Slide is visible.
Visible, sir.
Okay. Buoyancy and stability. This one slide.
Yes. Yes.
Okay. So basically, buoyancy is nothing but if you see this equation, what is written. Just I want to. If you see this equation, actually, buoyancy is nothing but the difference between two forces, the difference between two forces, which two forces, like let's suppose one body, I want to draw here one figure. It's a water body here. In the water body, one block is there. Let's suppose the thickness of the block is, let's suppose the t, or height is given h. So you know the from the very basic the force, that is the hydrostatic force on the top, how much, on the top how much force, like at the center of the body the force will, how much, rho g h into a. This is the force, that is the pressure rho g h, hydrostatic pressure, you know from the very basic. And from the bottom how much, from the bottom rho g h, and the height of this, height of the block t. plus T into A. So here nothing but written the at the place of H is taken in the figure was taken the S, and at the place of I have taken T, here is taken the S. So this thing here written, this is the bottom force, this is the bottom force, force bottom, and this is the top force. So these two force, here the talking, this line is talking about these two force, that is the bottom force and top force. The difference between these two force, bottom and top force, is known as the basically the buoyancy force. So here just the force, that is the bottom, and this one is the top. And when you will solve this simple equation, the algebraic equation, you will get these things. Rho gh, that is from here S and S, this term will be cancelled, only the rho g h a will remain. And A and H is what? It is the A volume of solid body. It is the volume of solid body, not the fluid and not the height. It is the volume of solid body. That is the area and the thickness of your body. So rho of fluid G and volume of solid body. So
But the thickness of solid body is T, sir.
yes,
The thickness of solid body is 3 T.
yes. Here is like here in this actually here what I have taken the example, it's a T, but in this above figure, because
Yeah,
this
yeah.
equation is written for the above figure. So if you correlate here, the H is equal to T here written. I have taken the, let's suppose here if you take the S and H similar thing, then the confusion will be, I have taken the similar.
I got it. Sir. I got it, sir.
Yes, so here H, here S, and here S plus H, right? So the similar thing. So this is the expression for your buoyant force. If some equation, if some problem is given like that, so you follow this procedure and you will get the how much buoyant force acting on the body. So now this is a very important concept. So conclusion is that the buoyant force acting on the plate is equal to the weight of liquid displaced by the volume, displaced by the plate. So why plate is coming? Because in the expression of the buoyant force, what is that, the volume of solid is here, so that's why. How much fluid, how much weight of the fluid will displaced by a volume. Basically if you, this is the parameter for fluid and this is related to the body, and this is constant. If you combine these things, this will get the weight. Weight of what? Fluid. Weight of fluid. So unit, like the your buoyant force is equal to what? Weight of fluid by displaced by per unit volume. Basically if you have sometimes people forget about the concept, but you always remember, if you put some solid body in the water, then what will happen? Your body will keep some space. So how much space will keep is equal to the volume of the body. So like that you can remember these things. So nothing but buoyant force acting on a plate is equal to what? The weight of liquid displaced by the plate or displaced by the solid body, you can say. So this is the only what I was discussed. This is given. So the Archimedes, what was Archimedes was given. The buoyant force acting on a body of uniform density, definitely density should be the uniform for the body. Density immersed in a fluid is equal to weight of fluid displaced by the body, and it acts upward through the centroid of the displaced volume. It will be act through the centroid of the displaced volume, not the centroid of your body, centroid of the displaced volume. You always remember.
Can you repeat, sir? Center of the.
Yes, centroid of the displaced volume.
Yeah.
Centroid of the displaced volume.
Yes. Yes.
Whatever, let's suppose your body is this, and this body if you put in the water, then this much volume will be reduced by removed from, that is from your fluid.
Yes.
So this much at the center of this displaced volume, your buoyant force will be the act, and always it is the upward direction, right?
Yes.
Okay. So now coming in this very important figure. So you know these things. The buoyant force is equal to this rho z and the volume of your submerged body. Let's, before going on this, let's read these things. For floating bodies, that is these things, for floating bodies, the weight of entire body must be equal to the buoyant force. This is a very important concept. When your body will be float, when the buoyant force, that is the your from the bottom, whatever the net force is acting from the bottom, is equal to your the, where is the weight of the entire body. The weight of the entire body must be equal to the buoyant force. So this is written like that here, which is the weight of the fluid. Okay, which is the weight of the fluid whose volume is equal to the volume of submerged portion of the floating body. Here what is telling, actually you, in case of the floating body, your weight of the entire body, weight of the body and buoyant force should be the equal, and for that, which is equal to nothing but, which is the weight of fluid whose volume is equal to the volume of submerged portion of the floating body, that is the volume of this submerged portion. So it is written here like that, rho g and volume of submerged is equal to what, the weight of the your body. This is the weight of the body. We will calculate, how we will calculate the weight, that is the, you know, the from the formula, weight is equal to what, that is the unit weight is equal to weight divided by volume. So from here you will calculate the weight is equal to what, that is the, this is represent the rho z, so rho z into v. So this is the v, nothing but this is only written w, that is the weight of the body is equal to this. So from here simple, submerged by the total is equal to these things. So what is mean that here it is written, therefore the submerged volume friction of a floating body is equal to the ratio of the average density of the body to the density of fluid. Okay. Therefore, the submerged volume friction of a floating body is equal to the ratio of average density of the body to the density of fluid. So, from here you can always remember. Note that when the density ratio is equal to or greater than 1, that is these things, your rho of the body and rho of the fluid If it is greater than 1 means what? Your body, the density of body will be the greater than density of fluid. If this case, then what will happen? And here the this rho is represent the density of body. If it is greater than, then your body will be the sink in the water. If it is equal, then it is suspended in the your in case of suspended in the liquid. And if the your density is less than body density is less than the your density of fluid, then what will be the floating condition? You know, the dry log is dry wood is floating on the surface because of this condition. And the stone is sink due to the because of the stone density is very very much than water. And you know, the sand case, if sand is suspended condition sometimes, so in that case these things will happen. So similarly, we'll move on the, and you know, the already the balloon thing, what is written, if I read, then you feel more example on that. The al- the altitude of a hot air balloon is controlled by the temperature difference between the air inside and the outside of the balloon. Why temperature related here the air? Because of air density is related to the your temperature. If temperature will more, density will be reduced. That is the hot air having the air that is the hot having less density than the cold air. So hot air will be always try to move upward direction. So inside the balloon is what? Hot air is here. So it is try to move upward. So due to this temperature difference between the air, so what will happen? And if hot air will be the try to move upward, then in that condition your balloon is floating in the air. So when the balloon is neither rising nor falling, the upward buoyant force is exactly balance the downward weight. Whatever the upward buoyant force is acting on the balloon, it will be net exactly whatever the weight of the balloon or whatever the human is here. So now stability of immersed and the floating body. This is very very important thing.
In the previous case, sir, it will be suspension. Will be how what will be suspension in that case?
Yes,
It
if
will be similar to
it is written, if in the case of suspension, what will happen? The weight of the your balloon and the force from buoyant force actually will be the equal. This is the actually
so.
I actually
Uh,
some you just if have you seen this helium balloon? Initially
yeah,
balloon, yes, initially balloon is below, and that is on ground when we put in our hand. Then after just releasing, what will happen? It's go move upward and upward. After some time, it is not move the far upward.
right. Okay.
So what will happen? And at that altitude, your weight of balloon and the buoyant force is equal.
Equal. Right. Right.
Yes.
Thank you, sir.
Now coming on, this is a very very important here, and why we read this buoyance force and stability criteria. So because of the we have some designing of ship, and you know the basic boat designing and all, we follow these things very very accurately. Any other join, any other guys? No. Okay, no problem. So stability of immersed and the floating body is what? Basically, it is an important application of the buoyancy concept is the assessment of the stability of the immersed and the floating body. That is with no external uh, attachments. Okay. Here the meaning is that the body is floating, whatever floating or immersed, it should be stable without any external forces. When we go with this concept, how we can stable these bodies, we will follow some concepts of science. What is uh, this topic is great important for the design of ship and the submarines. Figure is given here, you just see the ship is there and the lots of weight on the ship, but if the weight is more very high, then it is capable to float on the surface. Why? Because it designed very properly way in the properly manner. Definitely the ship having some load capacity, load limitation, but heavy load on the boat, but it is still floating because of the we have during the designing it is considered the stability criteria very accurate. So we use the classic for understanding of the stable and natural stable and unstable condition. We have one example, ball on floor example. Basically we see this example. So it is explained the fundamentally stability criteria. That is the in figure the three ball at the rest on the floor. It is ball is initially at the rest condition. The first case is what is written, that is the this case A B C. Here the case A, that is A is stable since any small disturbance, like we have applied some force from this direction, what will happen? Someone move the ball from right to left and generate the restoring force due to the gravity, and that result into the initial position. If in this shape, if the your ground level is, if your floor level like this shape, if you apply the force and after removing your force, what will happen? After some time your body will be at the same initial position. So if that type of condition is happening with this, then it is a stable condition. Okay, what is B is written? In case of B, is naturally stable. What is the mean of naturally stable? Because if someone moves the ball to right to left, it would stay it would stay put at its new location. It will be put at the new. If you apply the force from here, maybe the it will be stay on this new location, not at the in the previous one what was at the initial location, not possible. The regain the initial position is not possible in case of the naturally stable. This is written here, and it would stay put at its new location. Okay. It has no tendency to move back and its original location, nor does it continue to move away. Okay. So this is what the case B. And the case C, what is written? Case C is a situation in which ball may be at rest at the at a moment. Let's say at a time t, ball is an rest condition, but any disturbance, even an infinitesimal, that is a small one, if a small one we put the disturbance, what will happen? The ball to roll off the hill, the ball, what will happen? The ball will be the roll off hill. So it will never, it does not return on the original position. So, and rather it diverges from it, and this situation is known as the unstable condition. So I think this is the only analogy, and we have the technical terminology regarding that. That is the your buoyancy force and the weight of the body. But this is for the how stable, natural stable, and the unstable things is there. Sometimes it is very important in case of gate exam also. Some question was regarding like what was we discussed previously, the buoyant force and your what we'll going to in the next next your slide. I have some concepts. That concept is very important for your exam point of view also. So it is not appropriate to difficult discuss the stability for this case. Okay, this is how for an immersed or floating body is static equilibrium. The weight and the buoyant force acting on the body balance each other, and such bodies are inherently stable in the vertical direction. If an immersed or naturally buoyant body is rise or lowered to the different depth in an incompressible fluid, the body will remain in equilibrium at the location. So here what is written, what is telling in this figure, basically, from here you can just, if you, okay, let me read one line, then I will discuss. If a floating body is raised or lowered somewhat by the vertical force means your buoyant force, the body will return to its original position as soon as the external effect is removed. Therefore, floating body possesses vertical stability. This is talking about the vertical stability. If your body regain its the original position, this is the vertical stability criteria. While an immersed naturally buoyant body is naturally stable since it does not return on the initial or original position after a disturbance. The rotational stability of an immersed body depend on relative locations of the center of gravity and the body and the center of buoyancy, that is B, which is the centroid of the displaced volume. An immersed body is stable if the, this is very important line from here very important. An immersed body is stable if the body is bottom heavy, and thus the G point is uh, directly below your point B, like figure 1. So what is telling, I will give some example, physical example, you can feel actually what this three figure is telling. The first figure is telling you that if you have some body like that, your center of, let's suppose you are going to design something, and if you want to put your center of gravity, that is from, this is the axis, this axis divide the body in two part. If you want to put your center of gravity below this line, what you will do, you will put in the bottom, like here you will put this in the bottom, more dense material than the above, more dense material than the above. If you design like that, your center of gravity will be below. In the just opposite, if you put the heavy dense material on the above, what will happen? your center of gravity will be the shift above. The center of gravity, here I am talking about the center of gravity, not your the center of your shape. That is so here we are talking about the center of gravity. If situation like that, then what will happen? Your center of or center of buoyancy is depend on what? Center of buoyancy is depend on the volume of your whatever the body, volume of your body. It is not depend on the density of the body, it is depend on the volume of the body, your center of buoyancy. If you want to if you want to, if you try to design something, your center of buoyancy will be above than the same than the center of gravity. What you will do, you will put the dense material in the below side from the center. When your body will go inside in the fluid, what will happen? Your center of buoyancy will be the above than the center of gravity, and this condition is the center of and this condition is the stable condition, because as if some forces like the wave of water from here will happen, what will happen? Your weight from the below side is more, so there is no chance to rotate this body. If your weight is upper side, what will happen? The more is chance to rotation of your body in this direction or in this direction. But in this case there is no chance to rotation of your body. So this is the your, I think what I'm trying to say, Pradeep, you are getting.
Yes, 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 sir. Yeah, very simple. Yes,
Yes.
perfect. Yeah.
So this is very very important during the design. And okay, now we'll move and what is written here in point B and C, let us see. Okay, if your if you have designed some like that, your buoyancy and your gravity, center of gravity is meeting one at a same point, what will happen? It will be the natural stable condition. So this is the condition for your submerged body. Now we'll move on the floating thing. In case of submerged, if you want to, like you are going to design submarine, submarine is always in the submerged condition. So what you will do for stability of submarine, you will do your center of gravity is always below the center of buoyancy. So the body will be stable automatically. So this is a rotation kind of thing. During the rotation, what will happen? So here what is written? Let us, very very important thing. Rotationality is also important. We know the how why rotationality, that is the rotation thing happen in the body. Let's just see. What about a case where the center of gravity is not vertically aligned with the center of buoyancy? If you have designed some body, you're like that, like you have put the material, dense material in this direction, what will be happen? Your center
Sir,
of,
can you go back to the previous slide, sir? Previous slide, sir.
yes, you have doubt.
Yeah, a little bit, sir. So the third case will be unstable means center of gravity will be in
Yes,
the
above.
above.
Yes. What is meaning this slide? If you have your body like that and you have put it the dense
I got
material
it, sir.
this
I
side,
got it.
what will happen? Your center of, this is the your line which divide the, what will happen? Your center of gravity shifted in this direction. So what will happen? And your buoyant force is the shape is similar, like two bodies there, similar body, and this is not, this is wrong. If you have the two body, and in this you have put the dense material below, what will happen? Your, let's say the buoyant force is acting here for a stable condition, and G your is here. Buoyant force is always acting here because of buoyant force is depend on shape of the body. Shape is volume is similar V1, and this is V2 is equal to V1 is equal to V2. The shape is similar. What will happen? The rotation, because this is aligning with your buoyant force and your weight of the body is aligning in the in same line of action, so there is no rotation. But in this case, rotation. Why rotation? Because you have put this material, this side is more. So if you have design like this, then what will happen? Just see. It is not appropriate to discuss the stability for this case, since the body is not in the state equilibrium. Why it is not a state equilibrium condition? In the other words, it cannot be rest and would rotate towards its stable state even without any disturbance. Without any disturbance, it will be rotate because of your center of gravity and center of buoyancy is not in the line of action, the similar line of action. If you put like this type of material in the water, what will happen? It will be always rotate. Now coming on the, or after rotation, it might be let's suppose if you put the your, this is a water body. If you will put your body like that, what will happen? This thing, after rotation, this thing will go, what will happen? Your center of gravity coming in the below and buoyancy will be above. Buoyancy will be the above, and this, at this condition, it will be the stable, but it will be rotate. After rotation, maybe the half rotation of half rotation, or maybe the 2 by third rotation, it will be the stable condition. But it will be rotate. But your ones like ship and submarine or your will rotate, then what will happen? You know all very well.
So
So,
the V forces, V will be always in the center of the mass, center of the this material. Like,
no, no,
or,
no. Why? Because why it is? Because your shape is like that.
yeah,
So that is why it is so represented
I
on
have
the
been,
center. If
no, I
shape
got
is
it.
like that,
All right, okay, okay,
if
yeah,
shape is like that, there is no. It is not the same. It is not on the center.
right,
Okay.
right.
Okay. Now we move. I think if you guess if you guess some, I think, have you visited any river, Pradeep?
Yeah, yes, sir, yes.
If you visited any river, then some boat you have seen or
Yeah,
not?
I have already
Yes,
given.
if you have seen some boat in the below part, you just remember the what they do. The fisherman is putting the some steel part, that is a iron, that is a material part at the
Yeah,
place of wood. This is the reason behind it, because the because they try to increase the weight of the your bottom weight, so that's why your center of gravity is always below the center of buoyancy. So
right,
this
sir.
is the reason.
Sure.
So now we move on the next in the floating thing. Well, this is very very important also. Okay, the rotational stability criteria are similar for the floating bodies. Again, if the floating body is bottom heavy and thus the center of gravity is directly below the center of buoyancy, the body will always be stable. This is the condition. This is the similar condition than your the previous one. But unlike the immersed body, a floating body may still be stable when G is directly above the B. This is the condition. In case of the floating body, If G sometimes above than B, this is also the stable condition. And if your G below than G, this is the stable, it is naturally it will be the stable. But in case of stable, this one also is stable, this one also is stable. In case of floating body, in case of floating body, this is the, this represent the up and this is below, up and below. So if you see here, your in first case your G is below than B, and in this case your B is your G is above than B. Okay. So in floating case, these two case possible. You remember, I think this is important point. You maybe see in some exam also. So then what is it? This is because why it is happening in case of the floating body? Because of this is because the center of displaced volume shift to, why this is because the center of displaced volume shifts to the side to a point B dash during the rotation disturbance, while the center of gravity of the body remains unchanged. Oh, it is written here, if the some rotation is happening, then what will happen? Your volume will be, may sometimes it will be increase or sometimes be decrease. And you know the center of buoyancy is depend on the volume. If the volume is increased, then it might be chance to the your shifting of the, you know, the if the body is rotating, what will happen? This portion is maybe the this much portion increase from, that is the above the water, and here the some portion is below the water. What will happen? Then what will happen? Your, and you know the buoyancy point, that is the your point B is depend on the volume of the body. So your, definitely your volume is changed, definitely your B point will be the change. It is written here. This is because of the centroid of the displaced volume shift to the side to the point B, shift to the side to a point B dash during the rotation disturbance, and while the center of gravity G of the body remain unchanged. Okay. If the point B dash is sufficiently far, these two forces create a rotation, that is a restoring moment, not rotation, restoring moment, and return to the body its original position. Then what will happen? Just to see here, if your body is shifted, if one force is here, that is G, and line of action of B, that is the buoyant force is this. What will happen when your body is tilting in this direction? What will the rotation generated in this direction? So if rotation is in direction, so what will happen? After some time, your body will be in the stable condition, like this condition. That is the previous one. But and what is okay? If that is here written here, sufficiently far means if the, that is the your line of action is this. So the, you know the rotation thing, that is a moment is equal to what? Force into perpendicular distance. Force into perpendicular distance. So this is written here. If the sufficiently far means is this. If the having some distance between that, then the momentum, the your moment will be more. If the, and moment will be more, it may chance to return on the original position. So this is written here. Now coming on the, a measure of stability for floating body is the metacenter height. Why metacenter height? Because
What is a
your,
meta center? meta center actually.
Yes, meta center height, because you see here the stable condition in case of floating body, that is the previous one what was we discussed, only center of gravity and the center of buoyancy. In that case your body, or if the center of gravity is below than center of buoyancy, this is the stable condition. But here the stable condition is not depend only on your B and only on your the position of B. Here the position is below and position is above. In both case your body will be stable condition. So that's why we are in the floating body, one meta center height is very important, and we focus on meta center height at the place of center of buoyancy. So this is written here only. A measure of stability for a floating body is the meta center height, that is the GM, that is the G and M, distance between the center of gravity and center meta center. Okay. The intersection point of the line of action of the buoyant force through the, and what is meta center point? It is written, the definition of the meta center point is this: the intersection point of, if you see the here body is there, that is your B point is here, and your body, that is the center of gravity action, that is the line is this, line is this. So where it will be the touch of the center of gravity line, this is the meta center point is there. Because why? This is the, this due to this difference between these two line, your moment will be the, your momentum thing is happening, that is your moment thing is happening. So that's why at the intersection point of the line of the action of the buoyant force through the body force and after rotation, let us reread. A measure of stability of the floating body is the metacenter height, that is GM, which is the distance between center of gravity G and the and the metacenter. And the intersection point of the line of action of buoyant force through the body before and after rotation. Okay, that is the before and after rotation. It is what was the previous one condition and the after rotation condition. This is the meaning. The meta center may be considered to be a fixed point for most hall shape of a small rolling angle up to the 20 degree. If the rolling angle is 20 degree, for that we maybe consider the meta center point is at the same fixed location. But what is written, a floating body is stable if point M is above point G. That is the written. If your floating body is, this is the very this line is always, you need to remember. In case of the floating body, your floating body will be the constant, that is the stable condition when the point M, that is the meta center point, when will be the above than the point G. Why? Because just you see here in the figure, B is visible. uh, Let me come on the
Yeah, visible, sir.
figure. B is visible.
Yeah, visible, sir.
Okay, so why? Because your meta center height is this, uh, at that point in case of B. So the rotation, whatever the moment is, will be generate, your force G force is this and B force is this. So rotation will this direction. This point you have understand. If your point is this, but if sufficiently, let's suppose your meta center, that is whatever the buoyant force, in the previous case what was the buoyant force and the weight of the, that is your center of gravity action, line of action was same. In the second case what was, your center of gravity and the buoyant was not same, but it was sufficiently large, sufficiently far from the this line, sufficiently far from the this line. But in third case, what is happening? This is not far from the more far from the this line. Then what will happen? This line of action of your buoyant force is meet below the G point. Then in this case, what will be happen? In this case, your body, that is the moment should be, you need moment in this direction, but your moment is like that. Then what will happen? Your body will be unstable condition and chances to sink your body. So I think Pradeep, you got this thing. What I was trying to understand, what I am
So
trying.
what is actually meta center? Meta center means center of what?
Yes, yes, definitely. I will. Sarif, Sarif, are you getting? Basically, the meta center is nothing but let us. In this case, there is no meta center. You have seen. In this case, there is no meta center, right? Pradeep,
Yes.
it is visible.
Yeah, yeah.
In this case, there is no meta center. But in this case, the meta center height is there.
Yes.
The meta center is height means what? If your center of buoyancy deflected from the this line is what? The line of action of weight, right? From this line, if your center of buoyancy is deflected, as in the second case, so center of, then what will happen? If your body will rotate like that, if your body will be rotate, then this line is always straight. This line is always pass from the, if you see, this is pass from this location, right? In the second case, it is also pass from this location. Your center of buoyancy is shifted from this line to this line, and if you draw the line from here, what will be happen? What will be? This will cut this line at some point, and where it will cut, this point is known as the meta center, right? Pradeep, you are
Yes, 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 yeah.
yes, your basically your meta center is defined. If you see here very carefully, your meta center is responsible for your rotation. That is the direction of rotation. In which direction your body will be rotate, it is depend on the meta center point. It is depend on the meta center. If meta center is below the G, then what will be happen? Your body will be rotate in this direction and it unstable condition. If your meta center height when will be the above from the G, when your point B will be the sufficiently far from this location, right? If this point B was very near to this point, what will be happen? If you draw the straight line, it may chance to cut from this location, right? Like the point like C. So this is the whole idea. Your meta center is it defined. Your meta center is defined in which direction your body will rotate. It may rotate in,
So the meta center should be always above G basically.
yes. If always if your meta center will be always above, then you will in the safe condition,
Yeah.
right? If it
Yeah.
is below, then you are not in the safe condition,
Yes. Yeah.
right?
Yeah.
So this is the
So
whole idea. Now the same thing is here. Here it is clear visible. The meta center is below, right? So if below the your momentum is in this direction, so your body will be unstable condition. So from this discussion, the conclusion is that if you want to design some floating body, you always remember or always try to keep it in this condition. Your G, if this condition is there, it is very you are very safe in condition, safe condition, right? But for that you need to put the heavy material. This, if your material is very heavy, your always center of gravity, but it should also the limitation how much heavy and how much, this is the research thing. Okay, so now we, oh, here it is given a ball in the trough between two hills is stable for a small disturbance but unstable for the large disturbance. If we put the very large force, it may chance to go this like this. So it is written only these things. So one very concept is here, the rolling, pitching, and yeah, what is this? If your body is rotating, here it is also one figure is there. This is the, if your, let's suppose this is body, and this your front thing, what is written, this front view, this front, you are see from, you are going to see this body from the front, so it look like that. You are going to see this body from side, what is it, this is look like. You are going to see the body from the top, it will be look like this. If your body is rotating in the direction, rotating about the direction of x, then it is the roll. If it is rotating about the direction of y, it will be the pitch, and if it is rotate about the z, then it will be the yaw. So let, I want to see some my hand movement on that. Yes, my hand is visible, Pradeep and Sarif.
Yes, sir, visible.
You just see, this is the body. If your body is moving like that, right?
Yes.
Let's so this is the ship. If your body is moving like that, and some, let's suppose in the my hand some people sitting, so what will happen, let me, this is the pen is there, pen is visible. Hello Pradeep,
Yeah, yes, yes,
pen is visible.
yes, yes.
If this body is moving this type,
Yes, yeah.
this is the rolling, right?
Yes, yes.
If body is moving this in
Yeah.
this way, in this way, like
Very-
up or down, in
Yeah.
this way, this is the pitching condition. Okay, and if your body is moving like
Right, sir. Yeah.
this is the yaw condition,
Yeah.
right?
Okay. Yeah.
So this is the very important concept.
Yeah. Yeah.
So we now move on the boundary layer approximation. This is the very important.
So can we take a break, sir? 5 minutes, sir.
Yes.
Can you make a little break, sir? 2 minutes break.
Yes,
What?
we'll we take the 5 minutes break and then we'll move on the next.
Right. Yeah. Yes, sir.
Yes. Hello, Pradeep, I am audible. Sarif?
Yes, sir.
Okay.
Yes, sir.
Okay, we'll start the boundary layer approximation, and basically I will give some why when the boundary layer approximation was introduced in the fluid mechanics domain. Then we'll start from solving some problem. And I have some slides you in the last I will show, and you take just a screenshot and keep read for your more information about this is a very important, this is a very important. And sometimes people are very interested about know the boundary layer approximation interview point of view I am talking. So it is in interview point of view, it is also very important, the boundary layer kind of thing. So I have lots of slide, you just take the screenshot, I will show in the last. But why boundary layer is important and when it is introduced, just one line is there for your motivation, just I want to show. Yes, so from the history perspective, what is written here, from a history perspective, by the mid of 80s, the Navier-Stokes equation was known. It was known, but could not be solved except for a flow of very simple geometries. So this was the historical point of view. Meanwhile, the mathematicians were able to obtain a beautiful analytical solution of the Euler equations, but of and of the potential flow equations for flow of complex geometry. Complex geometry solution was also, but as using the Euler equation and the potential. But their result were often physically meaningless. The result was meaningless. Hence, the only reliable way to study fluid flow was empirically, that is the with experiment. The previously only the reliable way what was the experiment. The you study the fluid mechanics with the experiment. This was the way. But the measure from here, a major breakthrough in the fluid mechanics occurred in 1904 when Prandtl, that is introduced the boundary layer approximation. So in 904 the boundary layer approximation was introduced by the Prandtl. From here the fluid mechanics uh, just I want to read before. The Prandtl's idea was to divide the flow into two regions. What regions? Uh, outer flow region, that is inviscid or irrotational, and an inner flow region called the boundary layer. Boundary layer, what is boundary layer? A very thin region of flow near a solid wall where the viscous force and the rotationality cannot be ignored. That is, let's suppose this is a wall and a very thin layer, let's a very thin layer. In this layer your viscosity and rotationality will be considered, and above this there is no need to consider these things. So it is written this above layer is known as outer layer. This is the outer layer. If this is wall, so this is written. Now in the outer flow region, we use the continuity and Euler equation to obtain the outer flow velocity field and the Bernoulli equation to obtain the pressure field. Alternatively, if the outer flow region is irrotational, we may use the potential flow technique discuss whatever we have discussed in the previous, and obtained outer flow velocity field. In either case, we solve for the outer flow region first and then fit a thin boundary layer in the region where the rotationality and the viscous force cannot be neglected. Within the boundary layer, we solve the boundary layer equations. Within the boundary layer, only this boundary layer, we solve the boundary layer equations to be discussed shortly. That is the in the below section we have. Note Note that the boundary layer equations are themselves approximation of the full Navier-Stokes equations, as we'll see in the previous in the coming slides we will see. So this is the whole idea about the boundary layer approximation. In 1904, the boundary layer concept was introduced by the Prandtl. Before 1904, the reliable way of study about the fluid mechanics was only the empirically, that is the pure experimental way. So this is the whole idea, and we have the lots of slide I have. You just take the screenshot. I will show in the screenshots. I will show in the last. Okay. So from here, this is the question number first. If you see the question number first, what is written? Uh, Pradeep, the question number first is visible.
Visible, sir, visible.
Okay, if it is visible, what is written? Question number first. If the velocity distribution in a laminar boundary layer, you know the boundary, I think the week 11 is already over and the week 12 is going on, right?
Yes.
Yes, so you know all, I think you know the all concepts. If the velocity distribution is in a linear boundary layer, a laminar boundary layer can be assumed a small u by capital U equal to y by del, the ratio of momentum thickness theta to the normal thickness, that is your delta, is given by. Here what is asking? Here it is asking the ratio of your theta, that is the momentum thickness, and delta. So formula of theta you know already. You just solve and tell me what is the answer of this question. So before within 2 minutes you just give your answer in the chat box, and then after I will explain. Sarif and Pradeep, you both please try to solve the question. Okay, So actually the momentum thickness, I think formula is that small u by capital U 1 minus small u by capital U. This is the capital U. So this is the whole. This is the your equation. So here infinity is means your it is represent the maximum limit. Your maximum limit is what? Delta. So the appropriate equation for this, now what is 0 to delta u by capital U 1 minus the small u by capital U dy. If you will put here this y by delta such type of equation you can expect in the exam also, get exam and your fluid mechanics exam also. So y by delta minus y square by delta square dy. If you will integrate, that is theta is equal to what? That is the y square by 2 delta y cube by 3 delta square. Your upper limit is delta and lower limit is this. If you put the limit, what will happen? Delta square by 2 delta minus delta cube by 3 delta square. And if your lower limit is 0, if you put the 0, there is no meaning. Whole term will be 0. So 1 delta is cancelled. So delta by 2 here minus delta square and here delta cube delta by 3. So if you will minus from this to this, what will delta by 6. So delta by 6. So your expression is delta by 6. So what is the asking the ratio of theta by delta? So theta by delta is 1 by 6. So the option number C is correct for this. Pradeep and Sarif, you got it?
Yes, 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 sir. Yeah.
If you have any doubt, please ask. Then I will move up further on the next.
No, no doubt, sir. Yeah.
Okay, okay, fine. Sarif is also telling. Now we'll move on the next. Oh, this is also I have put it some like the what is boundary layer thickness and what is the displacement thickness, what is the momentum thickness. So this thing and how you will calculate the procedure is also given. One this example is your related with the I have one your question related with this example 10. uh, when we solve the last, that is the last problem, when we solve the last problem, this will help lot. Or you can take the screenshot and you also try to. Now we'll, this is a displacement thickness, you know the formula of displacement thickness from your, and what is displacement thickness? Oh, from the figure and the definition you know what is let me read. The displacement thickness is the distance, it is distance nothing but is the distance that a streamline just outside the boundary layer. This is, let's say that this is your boundary layer just outside the boundary layer. Okay, just outside the boundary layer is deflected away from the wall due to the effect of boundary layer. So I think displacement thickness definition you got, Pradeep and Sarif.
Yes, yeah.
This is very very important because sometime people forget about the displacement thickness and the thickness of boundary layer. Thickness of boundary layer is nothing but that is the original thickness of boundary layer. How much it, the thickness of boundary layer is the function of x. It depend on the x. From here the thickness is different, here thickness is different, here thickness is different. And your displacement thickness is what? Displacement thickness is just above your the streamline, just above the boundary layer. The actually it is the displacement thickness, it is the distance that streamline just outside the boundary layer is deflected away from the wall due to the effect of boundary layer. Very very simple definition. So you
No,
always
so no,
remember.
not very clear, sir, actually. So,
Oh,
why it is deflected due to effect of
yes,
boundary?
here it is also, if you see the figure, it is very, very clearly visible. In this figure, the distance from this, the distance between this, it is the displacement thickness. You remember this thing, maybe this will be required. And the displacement thickness for the laminar flat plate, this is the equation. Sometimes it is the directly useful, but laminar, your flow should be laminar, not in the turbulent. In the turbulent
Can you
case,
say previous slides a little bit? Can you just show? Yeah.
yes,
So this is the display thickness is what is that, sir? Actually, there is that is pretty. So,
you
uh,
have any doubt on the displacement
so
thickness?
the straight line, the dot line is what? Dot line is the uh, actual flow of path or something. Streamline.
Where you have doubt in the displacement thickness, should
With
I?
this dot parts, what it is actually. The dot, there is a two lines are there. One is dotted, one is solid line.
Yes, yes. Okay, okay. No, no, it's from, actually, it is for the, just for representation. It is not look like that if you will go in the field condition. Just for the express the in the mathematical term. Yes, it is from the dotted line. It is from the dotted line. It started the displacement thickness. It is just above your boundary layer, right?
Yes.
Suppose you forget about the this, and here why it is dy, because of the you are looking the things in the y direction. That's why dy. This is your boundary layer, right?
Yes.
Due to this boundary layer, your, let's suppose the streamline was like that, right? But due to the boundary layer, this streamline, if boundary line is not here, then what will happen? Streamline will go straight, right? But boundary layer is present, what will happen? Your streamline may be suppose look like that. It should go like that, but it is like that, right? So the this displacement and this displacement, why happening? It should, it should go like that, but displacement is due to the boundary layer formation. So this thickness is known as the your displacement thickness. I think you got it.
Yes. Yes. So everywhere we will have a displacement thickness
Yes,
everywhere.
yes, for here
Yeah.
also you have the displacement thickness here also,
Yeah.
right?
Yeah. Yeah.
It is also a function of because it vary with the x, and the depth wise it vary with the y.
Yeah. Depth wise. Yes.
Now coming on, in case of the your laminar flow, this is the relation for displacement thickness, how you will calculate. Now moving on the next, so these are the only, the momentum thickness is what, shall I read the momentum thickness definition? Yes, let me read. The momentum thickness is defined as the loss of momentum flux per unit width divided by rho u square due to the presence of growing boundary layer. So this is nothing but the whole idea is that your boundary layer formation, if boundary layer formation is try to lose the momentum flux. Flux means here is nothing but the flux means you just uh, here assume the flux is used for the mass transfer, right? The momentum transfer we have seen, I think, the uh, previous I think session we have seen the momentum transfer, the meaning of. So here that is this is written only the your momentum flux means your momentum transfer talking about. The momentum thickness is defined as the loss of momentum flux, that is your momentum transfer per unit width divided by rho u square due to the presence of growing boundary layer. Your boundary layer is, just wait. Yeah, your boundary layer is growing from one location to another location. That is the growing, right? So during the here is written due to the growing of the boundary layer, your loss in the momentum transfer. So this is represented by thickness, momentum thickness. Simply the question is coming like that. What is represent the momentum thickness? It represent basically it represent the momentum flux loss due to the growing of your boundary layer. So this is the whole uh, concept. But per unit width and divided by rho u square, this is used for the pure, because momentum thickness is the having the unit of length. So for coming for unit of length we have divide the rho v square and all, but the physical meaning is that that is the how much the momentum of momentum flux is losses due to the boundary layer formation or boundary layer growth. So this is the whole idea. And the your equation is like that. Here infinity is this, infinity nothing but is the maximum your limit, lower limit or upper limit. The momentum thickness in case of laminar, you remember, turbulent flat power law, you know the power law is like that. Power law is this, u by this will I will utilize this concept in the uh, question answer, so that's why I am showing here. So now the second thing is here. So the boundary layer, in the boundary layer developed along the flow, the pressure decrease along the downstream direction, like that. The boundary layer developed along the flow, the pressure decreases along the downstream direction. Let's say here pressure is 10 unit, here the pressure is 9 unit, here the pressure is 8 unit, like that. It is unit means is nothing but the Newton per meter square. So just for your visualize, just for your feeling of the question, I have taken this mathematical term. The boundary layer thickness would be, it will be
So,
the increase
yes.
gradually, it will be the decrease or it will be the, what will happen?
Increase gradually, sir.
Yes, if the pressure is definitely reducing, then it will be the increase gradually along the, definitely. Now the question number 3 is the mean drag coefficient CD, drag coefficient mean. Here is talking about the average, right? The mean drag coefficient for laminar boundary layer. One thing was also given, laminar, right? Over the flat plate was this. Value is given 0.015 if all other flow factors remain the same, okay, and the length of plate is decreased by the previous one. Let's suppose the length was your, in the first condition your length was L, in the second condition your length is what, decreased by 1 by 4th, that is 1 by 4 L, that is L by 4, okay, to the original value, okay. The drag coefficient would be, then in the first case and in the second case, what will be the your drag coefficient? So this is the question. This is the first condition. So please try to calculate these things basically. Within 2 minutes, please solve. Then I will discuss about this question.
We have not studied as a drag force yet.
Yes.
Drag force we have not studied yet actually. Drag and lift is still to be covered. 12th week, sir.
No, no. This is in case of the boundary layer.
All
The
right,
boundary layer.
all right,
eh,
okay.
Okay. Oh, I think you have not. Okay. Let me discuss. No problem. So for that, basically everything is remain. So before we solving these things, let me show you the formula, because your formula is not required. Only if you know the relation, then you can solve. But for your sake of understanding, okay. As per the Blasius result for the laminar boundary layer on smooth plate, the local drag coefficient is given by this, right? But average drag coefficient is given by this condition. You just remember here from your CDF or CD is directly proportional to 1 by R. That is the Reynolds number root 1 by R. So with this concept, we will solve the above problem. Your CDF is directly proportional to 1 by R, that is the Reynolds number. So what will happen? Your Reynolds number is nothing but rho u L by mu, right? So everything is same in the previous, in the state question is given, only what is changing, L is changing. So CDF1 is directly proportional to, if everything is constant, then only L is remaining, L1. L first. L first is what is written, CDF1 1 by root L, and CD2 F2 is what, 1 by root L by 4. Equation 1 and 2 just for your sake of understanding. If we divide these things, then what will happen? CDF1 divided by CDF2 is equal to 1 by root L divided by 1 by L by 4. So cancel out. That is your root L by 4 divided by root L. So root L cancel, only 1 by 4 is, root 1 by 4 is remaining. So 1 by 2, that is your 0.5. Right. So CDF1 divided by CDF2 equal to 0.5. CDF1 and CDF2 is equal to 0.5. You need what? CDF2. CDF2 is equal to CDF1 divided by 0.5. This is the 0.015 divided by 0.5. When you will calculate, this is the 0.30. Your option number A is correct. So I think you got it, Pradeep and
Yes,
Sari.
yes.
Yeah. So boundary layer approximation or boundary layer chapter is very important for your exam point of view also and interview point of view also. And also if you are try to understand the fluid flow problem, the boundary layer sometimes very helpful. Now we'll move on the next question. This thing I will show in the last, you just take this. Now in this question, question number 4. So what is written? A flat plate with a sharp leading edge is placed along a free stream of fluid flow. Okay. One plate is placed. The local Reynolds number at 3 centimeter from the leading edge, from here to here, that is from 0, it is 3 centimeter. It is 1005 means here it is written that 10 to the power 5, not 1005. Okay. And what is the thickness of boundary layer in centimeter? Basically, the thickness of boundary layer you need to calculate. So please just within 2 minutes or 3 minutes, you just solve the question. Here the question is that you solve the boundary layer. Find out the thickness of boundary layer. Then after 2 minutes I will. I think this part is covered. Pradeep, thickness of boundary layer.
Yes, it is covered, sir. Very much.
Yes.
Yeah.
So thickness of boundary layer, you know, the depend on the Reynolds number. First you calculate the Reynolds, or Reynolds number is given. If your Reynolds number in the laminar case or within the critical range, you use the formula of laminar whatever the thickness of laminar flow case. And from that you calculate these things. We have the another session on 16, and one session I want to take also on 20. 20, is it okay for you, Pradeep? Friday?
No problem, sir. I am free in the evenings. Yeah.
Okay. Yes, from 6:30 I will start on Friday, that is on 20 October, 6:30 to 8:30.
Okay, sure.
You will get the reminder from the NPTL. No problem. Okay, now move on the solution part. So have you got the solution, Pradeep, or we'll discuss? Are you
One second, sir.
solving?
I, no, I can do it, sir. We can do it. Yeah.
Okay, if you are solving, please solve. By the way, in this problem, we'll use this formula: boundary layer thickness,
Yeah, yeah.
laminar
So,
flow.
yes, sir. Yes, I did the same thing, sir.
If you will use this formula,
There's some problem with the calculation.
okay, okay, no problem.
uh, it is not matching actually. So 1.4 something is coming.
Okay, your RE is given.
Yeah. So basically, it is like 4.91 into zero point zero 0.03 divided by 10 to the power 5.
Yes,
So it is zero point 0.4 something is coming.
yes, yes. So the option number is B is correct.
Yeah.
Now this table is very very important. If you want take a screenshot, please take a screenshot. Let me put it in the bigger size. And you remember these things here. Two turbulent, two option is there. One on the basis of 1/7 power law. This is 1/7 power law on the base of, and of, and second one is based on the 1/7 power law and the empirical data. This is combination of both empirical data and 1/7 power law both. So this is sometimes also important. Some question was related like that. You solve this problem based on the empirical equations. So you always solve using this. Sometimes you try to solve this problem using the 1/7 power law. Some problem is written, so you try to solve. Uh, that is the whole. What is asking? It depend on your problem. Okay, now this is okay. Now coming on the next question. What is the ratio of displacement thickness to the momentum thickness for linear velocity distribution in the laminar boundary layer along the flat plate? So here the displacement thickness to the momentum thickness, that is your delta star divided by theta, is how much? And the what is written here, your the linear velocity distribution means what? Small u by capital U and y by delta. This is the linear distribution. So you know the delta star is what? Delta 1 minus small u by capital U dy, and your theta, what is theta? 0 to delta small u by capital 1 minus small u by capital U dy. Put the value in this and you will get the solution. So should I solve or you will try?
We'll try, sir.
I think we have not much time, so
Yeah, 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 yeah.
just I
Okay.
want to put it 0 to delta and 1 minus y by delta dy, and for theta 0 to delta y by delta 1 minus y by delta dy. If you will solve these things, what you will get? y minus y square by 2 delta, your upper limit and lower limit, and theta is equal to what? You will get y square by 2 delta minus y cube by 3 delta. Your lower limit and the upper limit is this. After solving, you will get delta minus delta by 2 after putting the limit, and you will get the theta, your delta by 6, I think. Delta by 6. So when you will multiply, what will happen? Delta by 2 and theta is equal to delta by 6. You need these things. So delta by 2 divided by delta by 6. So your 6 by 2, that is 3. Your option number D is correct for this. Right. I think you got the procedure. Pradeep and Sarif.
Yes, sir, got it.
Okay. Now we'll move on the next question. The next question is asking about in the turbulent flow. Here is given the turbulent flow, not boundary, turbulent boundary layer on the flat plate. The velocity distribution is given by 1 by 7th power law, right?
Yeah.
If the boundary layer over the whole plate is turbulent, the ratio of shear stress tau 1 by tau 2 at two section 1 and 2 at a distance of leading edge, that is a turbulent flow is given, like here x1 and here 5x1, right? So here is tau 1 and here is tau 2. Your turbulent boundary layer is here. So ratio of tau 1 divided by tau 2, how much? You know your tau is directly related to your friction factor, your CF, and your CF is related directly proportional to 1 by, that is the RE to the power 1 by 7th, or it is 1 by RE by 5, 1 by 5 also. From the this, you know these things. I think from here not visible, so we'll move this. From the power law, this is directly proportional to your 1 by 7, inversely proportional to 1 by 7, and the CF inversely proportional to also 1 by 5. If you combine the empirical and the 7th power law, it will be 1 by 5. Only power law, it will be 1 by 7. So if we consider 1 by power law, then what will happen? RE, you know the RE is your, like CF is directly inversely proportional to 1 by, if we take this 1 by 7, RE, you know already the RE is rho V and L divided by E. So it is RE proportional to L. So here you can write the L 1 by 7. So your CF1 is directly proportional to tau 1 CF1 L1. Okay. So if you will solve these things, you will get your tau 1 is equal to tau 1 by tau 2 is nothing but your x1, that is your, if you L1 is below, then it will be the, that is your 5 x1 power 1 by 7 divided by x1 power 1 by 7. So you are getting how much? 5 to the power 1 by 7 if you do. How much you will get? Here is my calculator. Let me use the mobile for that. How much you will be get, Pradeep? You just tell. 5 to the power 7. 1.258. If you will solve using this 1 by 7 power law, your answer will be 1.258. And if you will solve you using the your empirical and 1 by power law, it will be how much? Divided by your 5 to the power 5. 1 by 5. 1.379. So both here option
We should
is
have only one. But so we should have only one, is it not? One answer.
yes.
We should have one answer basically.
Yes, yes. Here it is like when I was seeing in this question, the option was correct this one, but I don't know who is framing this question. But here it is clearly written your velocity distribution is given by 1 by 7th law, right? So
Yes,
if
sir.
it is 1 by 7th power law, if you so you must use this 1 by 7, right?
Yeah,
1 by 7 thing if you will use, then your option is correct. Option number A is correct for this, right?
yeah,
And question 7 is what actually written. Question 7 is very simple thing. What is the boundary layer thickness, that is delta is asking, when the flat plate of 15 centimeter and 45 centimeter long placed longitudinally, that is your length of plate is 45 centimeter and your width of the plate is like this and water is flowing like that, right?
yeah,
Okay. The density of your fluid is given this and the kinematic viscosity is given 0.9 and free stream velocity u is given 6 meter per second. So your density is what basically. So first you need to calculate your Reynolds number. Reynolds number is what? U in length divided by mu, right?
yeah,
Your u is 6, length is 0.45 and mu is equal to how much? 0.9 into 10 to the power 4 minus 4. We have put here all things in meter, right?
yeah,
So if you will calculate these things, you will get here 90, here 20, that is 2 and 3, 3 into 10 to the power 4. That is your laminar condition, right? For flat plate. If the condition is laminar, your boundary layer thickness is like that, right? So delta is equal to 4.91 divided by root under 3 into 10 to the power 4 into uh, your x. X is how much? 0.45. Your answer is how much? If you will calculate. that is the 0.13, right? There is
Yeah.
0.013. Option is there. Option
Yes.
D
Yes.
is
Yeah.
correct for
Yeah.
that.
Yeah.
So question number 8. The question number 8 is very very lengthy question, right? But how you will approach this question? For that, just first you take the screenshot of this question, question number 8. It is
Take it.
done.
Yeah.
Okay, for
Take it.
that I have one example. From here you can take the screenshot. Let me put it in the full view mode. It will be more visible. Visible, clear visible.
Yes. Yeah.
Okay, you take the screenshot. This step also. This next, this is also involved in this question. Or this is also involved in this question. If you solve this question, you feel what is boundary layer actually, how we calculate and all these things. This is also step 5 is also in the. So the whole idea is that the boundary layer thickness. So in the next session, we'll move on the next things, right? That is the next, I think, open channel flow I will take. And
Yes.
in the last, I will take the drag and lift.
Yeah.
Okay.
Yeah.
In the last, I will take the drag and lift thing. In the coming session, I will take the open channel flow. I think open channel flow is going on, right?
Yes, sir. It is correct.
And the last, I
It
think,
is
last
together,
lecture
sir.
of
As
the week 12 is
yeah.
about the drag and lift.
Yes. Dragon.
So we'll
Yes.
take on the next session like on Friday. On Friday, I will take the drag and lift. And if you have any question, you just write me mail, and we'll discuss on the last that is on 20th October your queries and drag and lift topic. But in the coming to session, I will talk the coming that is on 16. We'll talk about your open channel flow.
Right, sir.
Okay, then we'll meet again the next session. Okay, thank
Yeah.
you.
Yeah.
Bye bye.
Thank you, sir. Good night, sir. Bye
Okay,
bye.
thank you.